Maybe I'm with it now. Okay, we'll see. All right, so the plan is to finish 3.3. That won't take us very long. And then work on 5.1 today. But before we do that, I want to give you a heads up. Okay, it looks like I was looking at where we're at and how our schedule looks from here. So it looks like test 1 will be on Thursday, September 16th. That's what that's looking like. Okay. So got 5.1 today, and even if we don't get it finished, we'll finish it along with 5.2 Thursday. So then next Tuesday, so what's that? Today's the 7th, so next Tuesday will be the 14th. Will be our review day, and then that'll put test 1 on Thursday the 16th. Okay? So what'll happen is I will probably today, well, maybe tomorrow, I will post a practice test on Hawks. Okay? And it'll be similar to the test, so it gives you an idea of what types of questions from each section will be on there. Okay? You don't have to do the practice test on Hawks if you don't want to. It's not worth any points. Okay? It's just a study tool, so it's up to you how much time you spend on that. Okay? I'll set it where you can take it as many times as you want to, though. Okay? So just have that study tool there available for you. It'll be different problems every time you go through, like the practice section of Hawks is. And then on next Tuesday, a week from today, we'll review in class. Okay, so we'll go through. I'll print out a version of the practice test, and then we'll just go through. You can ask whatever questions you have on any of those that you're getting stuck on, and then we'll be ready to test on the 16th. Okay. Questions about any of that? And I think I've said it before, but just in case, I will give you a formula sheet so you don't have to memorize formulas. Okay. You do have plenty that you have to know, but you won't have to memorize formulas. So like mean, you might not need a formula for, but standard deviation we're doing in our calculator, so we really don't have all that, but the other stuff I'll give you. Okay. So no questions? Okay. All right, so picking up where we left off, we said if we find the 3 quartiles, and I'm gonna go back a slide here. We find the 3 quartiles of a data set, and then we add in the minimum and the maximum. That's what we call a 5-number summary of a data set. And I told you the next thing we were going to look at was that if we take that 5-number summary and turn it into a graph, we get what's called a box plot. Okay, so, well, okay, so we'll skip that. We'll get what's called a box plot. Okay, so it'll look something like this, and we'll walk through what each little part of the box plot means, what it represents, in just a second. Okay, we do have one more thing to talk about I forgot about. Okay, it's called the interquartile range. Okay, that sounds really sophisticated, but all we're doing is we're taking Q3 and subtracting Q1. Okay. So we're just figuring out the range between Q3 and Q1, or the range of the middle 50% of our data. Okay. So let's go back to our last data set here. We've got data set B. So we wanted the interquartile range here. We've already found the quartiles. So for this one, it would just be 79's Q3 minus 67's Q1. We get 12. Our interquartile range on that one is easy. Okay. Q3 minus Q1. All right. Now we're ready to get all into the box plot stuff here, maybe. Man, that's the only thing about Monday holidays, is that then Tuesday turns into Monday. Does it do that for anybody else? Can have a Monday on Tuesday. It does for me. Okay, let's see if I can get this thing unfrozen here. Mine's upside down. I'm waiting on it. There we go. Okay. All right, so I'm gonna walk through making a box plot. Okay, it'll only take a minute. So what we do, we find our 5-number summary. I got all the step-by-step stuff in here. You really don't need it too much. You just want to be able to read the box plot. Okay, so here we've got the 5-number summary for some data set. We don't have the data values, but we've got the 5-number summary. Okay. So remember what those 5 numbers are. These are in order, so this would be the minimum, Q1, first quartile, Q2, second quartile, or what was the other name? Remember? The median, also known as the median. Okay. Q3, the third quartile, and then the maximum. Okay. It's our 5-number summary. So all we have to do to make a box plot, because we need a number line, and then on the number line we put a little dot or a dash where each one of our 5 numbers are. Okay. So here's our number line on this one, and I've got a little dash where each of our 5 numbers would fall. And like the minimum was like 12 point something, so a little bit above 10 there. Okay. So the next thing we do to make our box is we're going to connect Q1 with Q3. Okay. So we just draw a line to finish making the box on top and bottom, and to connect Q1 with Q3. And then the median, or Q2, is a line that goes through the box. And then the only other thing we have to do to make the graph is we connect the box to the minimum and the maximum. Okay, so we just do that with a line and end up with something like this. Okay. That's a box plot, or sometimes you hear it called a box and whisker plot, because those last lines we make, sometimes they get called the whiskers. Okay. So what all can we tell from a box plot? We can get an idea of the shape of our data. Okay, remember our 4 basic shapes: uniform, which you really don't see on a box plot. Then we got symmetric, skewed left or skewed right. So if our box is kind of far over to the left and we've got a long skinny whisker over on the right side, that would be skewed to the right because we have the skinny whisker on the right. Okay, that kind of stuff. The length of the box. If we wanted to figure out how long the box was, we would take this number, which is Q3, and subtract this number, which is Q1. So that's the interquartile range. Okay, the length of the box is the interquartile range. And then we said already the median's the line through the box. All right, so pretty common graph. You may not be as familiar with these as some of the other ones we've seen, but box plot does get used quite a bit. Okay, questions there? How to make the box plot? What the different numbers are? Okay. Here's one that's a little bit different. Sometimes people put kind of their own twist on different graphs. If you look over here on the explanation, one thing they've done on this one is instead of using the maximum and the minimum, they got the 90th percentile and the 10th percentile on there. Why do you think they may do that? So instead of the 100th percentile or the maximum, they've gone back to the 90th percentile up here. And then instead of the minimum, they've gone up 10% to the 10th percentile. What do you think they might be trying to get rid of on the ends? What types of extreme data values can we have sometimes on one end or the other of our data? Outliers. Okay, so they're kind of trying to cut out outliers on this graph. Okay. And then they give a little something extra too. They put a dot where the mean is. That's not standard. Okay. One other thing that we can see comparing these box plots here is we can also get an idea of the standard deviation of the data set from looking at the boxes or the box plots. Okay, because remember, a large standard deviation means our data is more spread out. A small standard deviation means it's more compact. So like if we look at these two, we're looking at the phosphorus concentration in these different river basins. Okay. Okay, so maybe we wanted to compare the second one, the Ohio-Tennessee River Basin, to the third one, the Missouri River Basin. Which one does it look like has a larger standard deviation? Yeah, Missouri, because it's way more stretched out. Okay, it's more spread out, so that implies a larger standard deviation. Okay. So something that you can notice there. All right, I think that's about it for box plots. Yeah. Okay. So one more idea in this section. Okay. There. And that is this idea of a standard score. A very, very important idea. We'll rely on this idea a lot moving forward. Okay. And the reasoning they give us for thinking about these things called z-scores or standard scores is that sometimes we may want to compare data values from two different populations, okay, to see where they lie within their respective data sets. Okay. So that's difficult. Okay, so maybe we've got one data set from population A over here, a data set from population B. We can't make a direct comparison, right, when we're just looking at the numbers, because we've got this population has some mean and some standard deviation. This other population has some mean and some standard deviation, and they may not be anywhere near the same. Okay, but sometimes we still want to compare the two data values. Okay. So this idea that we're going to look at of calculating a standard score or a z-score lets us make that comparison. Okay. So what this standard score gives us, okay, is it tells us how far a particular data value is away from the mean in terms of the standard deviation of its home, of its population. So we're saying how many standard deviations is this data value away from the mean of its population. Okay. So let's look at the formula. That might not seem all that useful to you now, okay, but it is. We'll see some applications as we move through the class. Okay, so if we look at the formula, it says if we want to calculate one of these z's, a standard score, easy formula. We're going to take our data value, that's just the x, whatever data value we're wanting to change, subtract mu. Anybody remember what mu is? Mu is, you gotta learn them. Okay? Gotta learn them because that's part of the vocabulary for the class. You don't want to get tripped up having to spend a lot of time thinking about what mu is. And mu is the population mean. Okay? And then we'll divide that answer by lowercase sigma. You may remember it. Population standard deviation. Good. Okay. Anybody heard about, I'm almost sorry to bring it up, okay, but anybody heard about the new coronavirus variant going around? What's it? Delta's the one we're dealing with now, but mu. Okay, so if nothing else, I'm kind of glad I get to see a stat variable come into play there. Okay. If we got to deal with it, we might as well have math related ones. Okay. They're not saying it's going to be too terrible right now, so hopefully we get past Delta and we'll be done with it. We'll see. All right, so we take our data value, subtract the mean. So how far away is it from the mean? But then we're dividing by standard deviation. Okay. That's our standard score. If you're putting it in your calculator all at once, you'll You'll want to put parentheses around the top because we want to subtract first and then divide. Just be aware of that if you're getting the wrong number in your calculator. Okay. So we also have a sample version of the formula, but mathematically it's the same thing. The only thing that changes is our labels, because remember we're very intentional about saying where our numbers come from. Did they come from a population or from a sample? So here we're still doing the same thing. It's our data value minus the mean. It's just a sample mean this time, so x bar divided by the standard deviation, but this time it's sample standard deviation, so it's S. You're not going to get messed up on the math on that because the formulas do the same thing. They just have different labels. Okay. All right, so let's look at using this thing. All right, this one says that the mean score on the math section of the SAT test is 500 with a standard deviation of 150 points. What is the standard score for a student who scored a 630? Okay. So we have an SAT test score that we want to change to a standard score or a Z-score. Okay. So to do that, we need to know two numbers about the population it came from. We need to know the mean. It tells us the mean score here is 500. I'm going to call that mu. And then the standard deviation is 150, so I'm going to call that sigma. And then the data value we're trying to change to a Z, to a standard score, is 630, so that will be our X in the formula. Okay. So then for Z's, I put a bar through my Z, so if you see that, no, I just got a little bar through it so I don't get it confused with a 2. You don't have to do that, but that's just my habit. Okay. So it's the number we want to change, 630, minus the mean, 500. We're going to divide that by the standard deviation, 150. Sometimes these come out nice and even, but most of the time they do not. So our standard here, and you'll see why later. Okay, but in this class, we're going to round all of our standard scores to 2 decimal places for the most part. So let's see what we get. 630 minus 500, and then divide that answer by 150. So here I get 0.866 repeating. So we'll round that to 0.87. Okay. The calculation's not hard. What's that number telling us? Okay. That number is telling us that this SAT score of 630 is 0.87 standard deviations above the mean. Okay. And how do I know it's above the mean? Well, what would it look like if it was below the mean? It wouldn't be positive, it would be negative. Okay? So 0, if you plug the mean in for our X, we'll have 500 minus 500 here, so that would be 0. So the mean is at 0. A positive standard score, Z-score, is above the mean, a negative is below. And the units are standard deviations. Okay. And I'll make you think back to last time a little bit. Thinking about empirical rule here. If this score is at 0.87, would you consider that score really unusual or not? What's the empirical rule tell us? It tells us within 1 standard deviation of the mean, what percentage of our data is in there? About 68%. This score is between -1 and +1. So it's in there with 68% of our data. So This is a typical score. It's not unusual. Have to have a large or a small z-score would be on the extreme ends. This one's there in the middle somewhere with all the rest of the data, so pretty typical. Okay. Questions on that one? Easy formula, that's the good news, right? Easy formula. And it's a good thing it's easy because we're going to end up using this formula a lot in here. Okay. All right, one more. Okay. So on this one, we're actually going to use the standard score to make a comparison between two data values. Okay. Let's look this one over. It says Jody scored an 87 on her calculus test and was bragging to her best friend about how well she had done. She said that her class had a mean of 80 with a standard deviation of 5. Therefore, she had done better than the class average. Okay. Her best friend Ashley was disappointed. She scored only an 82 on her calculus test. Personally, I would be happy with that. The mean for her class was 73 with a standard deviation of 6. We want to know who really did better on their test compared to their classmates, compared to their peers. Okay, so it's not meaningful to directly compare Jody's 87 with Ashley's 82 because those data values are coming from two different populations. They're in two different classes. Okay. So what we need to do in order to make a direct comparison is changing both to standard scores. Okay, change both to Z's. Okay. All right, so we'll do that. We need to use our Z formula twice here. I've got them color coded for us. So Jody, we change her test score to a Z. She scored an 87. That's the number we want to change to Z. That's our X. I said her class mean was 80, so minus 80. And the standard deviation for her class was 5. Okay, so if we do that calculation, should get 1.4. And just to get in the habit of using two decimal places, I'm going to call it 1.40. Okay. For Ashley's raw score was 82. Ashley's class average, her mean, was 73. And that class had a standard deviation of 6. So if we do the calculation here, you get 1.5. And then again, I'm going to write it 1.50. So if we're comparing them to their respective classmates, who did better on their test? Ashley. Okay. So she scored 1.5 standard deviations above the mean. Okay. And Jody scored 1.4 standard deviations above the mean. Okay. Even though Jody's raw score was better. Okay. So that's the kind of information that we want to be able to pick up sometimes. And that's one thing standard scores are going to do for us. Okay. Have you ever heard the phrase, you don't have to run faster than the bear, you just have to run faster than what? Than your friend. You don't have to run faster than the bear, you just have to run faster than your friend. So a lot of times when you get into upper level classes, the raw score doesn't mean that much, okay? Because things get scaled and all that. You just don't worry about your raw score too much. You're just trying to do better than your peers. Okay, right or wrong, that's how it works out. Okay, I made a 43 on an exam one time, and it turned into a 76. So I was kind of in the middle on that. All right. Questions there? Okay, that's it for 3.3. We didn't have much left there. Okay, 5.1 is our next section. So nothing in chapter 4. We skip over it in here. Chapter 4 is a lot about probability rules. Like how do you add probabilities together and things like that. We don't have to have a lot of that for the things that we do in 204. And we do need a little bit of knowledge about probability. And that knowledge we're going to pick up in these two sections in chapter 5. Okay, so section 5.1, called discrete random variables. So part of that we've heard about before. Variable, we just know something that its value changes. Discrete, we're more familiar with. What does discrete data mean? If data is discrete, you remember what that is? We had discrete data and we had continuous data. What was the difference between those two? Continuous data is when we have some type of measurement, and it can take any value, it can be as precise as we want to be. But discrete data, what types of values are those normally, do you remember? Yeah, we're normally counting, so we say discrete data can only take on certain values. Usually when we're counting, it's whole numbers. There are sometimes when we count weird, but usually we're only taking on whole numbers here. Okay? The random part we've got to talk about a little bit and get a good definition for that. Okay? So when we talk about a random variable, what we mean is we have some variable and its value, numeric value, is determined by some type of probability experiment. Okay, so what is that? That's when we have some type of event where we don't know what the outcome is going to be until we actually do the thing, we actually do the experiment. We can figure this probability experiment because we can figure out the probabilities. We know, there's this % chance this is going to happen, this % chance this is going to happen, but we don't know the actual outcome until we do the experiment. Okay? The first one we're going to look at is flipping a coin. Okay? There's two possibilities when you flip a coin, right? You get heads or tails. We can figure out the probability. If there's 50% chance you get heads, 50% chance you get tails, but we don't know what the actual value is going to be until you do the coin flip. And here it says whose numeric value, so there we would call like heads 1 and tails 0 or something like that. We turn it into a random variable. That's all that is. Do have a little bit of weird notation stuff that goes along with this that we don't see since we skipped chapter 4. So here as we go through these two sections in chapter 5, okay, when you see a uppercase X, okay, that's going to mean we're talking about a random variable. Okay. So like the outcome of our coin flip would be an uppercase X. If you see a lowercase x, we're talking about the specific value that we get when we do the experiment. So you could think about lowercase x being like heads or tails or really 1 or 0. We'll label it that way. So what you're going to see some notation that looks like this. So what this is saying is this is the probability, and if you got p with parentheses, probability that our random variable, big X, equals some little x, some specific value. Okay. So you might see it like this. You'll see like And this is just saying the probability that our random variable takes the value 1. Okay. If you see the multiple x's in there, that's what's going on. Okay. So our goal in these two sections is to talk about these things called probability distributions. Okay. So that's our next definition here. Okay. And there's several pieces to it. Okay. So probability distribution, it says it's a table or a formula. Okay. For us, we're mostly going to be dealing with tables. Okay. You can have a formula that gives you the same thing, but we're mostly going to be just looking at tables of values. Okay. And that table needs to give us every possibility for a random variable and the probability of that possibility. Okay? So the way it's written up here, it gives the probabilities for every value of a random variable such that the following properties are true. We got to have two things. You got to have two properties. And you'll have questions in Hawks that give you a table, and the question will say, is this a probability distribution? So you got to check these two properties and see if both of these hold. Okay. So property number 1 says that every probability that's in the table is between 0 and 1. And it says inclusive, so that means it's okay if it's 0, it's okay if it's 1. And that makes sense because when we're working with probability, like this is the decimal version, but if you change these to percentages, what this is saying is that each probability needs to be between 0% chance and 100% chance. Okay? So typically that's how we use probability, okay? Usually between 0 and 1. And this is just notation that says the exact same thing as the words. It says the probability of our random variable taking some particular value is between 0 and 1. And then property number 2 says the sum of the probabilities. So if we take our table, we add up all the probabilities in our table, we should get 1. So in practical terms, that just means we have all the possibilities covered. Okay. And then the notation again says the same thing as the words. It says if you add up all these probabilities, you should get 1. Okay. Okay. So let's make one of these probability distributions. Okay. And hopefully this will make more sense. Okay. Ready? Okay. So let's look at this one. And we'll walk through this one together. This one says create a discrete probability distribution for big X. And we want big X to be our random variable that counts the number of heads we get when we flip 3 coins. Okay. So making the table, we need to have a row or a column. You can do it as a column too, but I'm going to do a row for the different values my random variable can take. Okay. So what values can our random variable take here? So what we're doing in our experiments, we're going to flip 3 coins, and our random variable is going to count how many heads we get when we flip those 3 coins. So if we flip 3 coins, what are the possibilities for how many heads we get? We could get a minimum of, if we flip 3 coins, the minimum number of heads we could get is 0. Or it's possible we could get 1 head and 2 tails, or 2 heads. Or the maximum we could get, since we're flipping 3 coins, we can't get any more than 3 heads. Make that a little smaller. Okay. So those are all the possible values that our random variable can take, because those are all the possibilities for how many heads we get when we flip 3 coins. And the other row, we need the probability of each one of those things happening. So the way you'll see that written is probability that big X equals little x. So this is saying the probability that we get 0 heads, or the probability that we get 1 head, or 2 heads, or 3 heads. So to figure that out, we're flipping 3 coins. We could calculate it, okay, but we don't have to be that fancy or that sophisticated. One way you can figure out these probabilities is just to list out all the possible outcomes. Okay. So here, I'm just going to write them all down. Okay, if we flip 3 coins, one possibility is that we get heads on all 3 coins. And I'm going to be kind of systematic about writing these down so we don't miss any. I'm going to say the next possibility is that we get heads on the first 2 and tails on the last one. Or we could get tails on the second coin, or tails on second and third. So if you see what I'm doing, I'm alternating heads, tails every time on this last row. And the second row, I'm going heads, tails, and it'll start back over. And on the first row column, I'm going heads, and then it'll be tails next. Okay. So I wrote too big. Okay. So next one will be tails, heads, tails, heads, tails, heads. I got one more. I guess I'll stick it off to the sides. Tails. So if you check it, those are the only possibilities. And how many of those do we have? How many total possibilities do we have for our experiment? 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we only have 8 possible outcomes. And now we just need to count out of 8 how many of those fits these possibilities for our number of heads. Right? Okay, so the first one we want how many of these situations give us 0 heads. Yeah, we only got 1, tails down here. Okay. There we got 1 possibility of getting no heads. So that's 1 out of, we said we had 8 total possibilities. Okay. And for 1, we just look through and see how many of our possible outcomes only have 1 head. So let's see. This one, right? Heads, tails. This one, tails, heads. And this one, tails, heads. Those all have 1 heads. So our probability for getting 1 head is 3 out of 8. That's right. Okay. Do the same thing for 2. So this heads, tails. That's 2 heads there. Heads, tails, heads. That's 2 heads. And then tails, heads. So again, we got 3 out of 8. And then how many ways can we get 3 heads? Just 1. Heads. So 1 out of 8. So this is you could write them as decimals too. Okay, that's fine. This is a probability distribution, this table. And how can we be sure? We have to check our 2 properties. Property number 1 says each probability is between 0 and 1. Okay. 1/8 That's between 0 and 1. That's 1.25 as a decimal, or 0.125, sorry, as a decimal. 3/8, that's also between 0 and 1. That one is. That one is. So they're all between 0 and 1. So property number 1's good. Mark it off. Property number 2 says if we add all the probabilities up, we get 1. Okay. So here 1/8 plus 3/8, I know it's a fraction, it's 4/8. Plus 3/8 is 7/8. Plus 1/8 is 8 out of 8. 8 out of 8 is 1. Okay. So this is a probability distribution. Okay. Questions on checking that? Most of the ones in Hawks are just going to give you the table and say, is this a probability distribution? And you say yes or no, and then you have to pick why. So it's just checking those two properties. Okay. There's our first probability distribution. Okay. Once we have a probability distribution, we have a couple things that we can calculate that gives us good information. The first one of those things is called the expected value. Let's take a look at that. Our symbol for expected value, it looks like a function if you're familiar with function notation. It's just uppercase E, and then in the parentheses we have uppercase X. So E of X is what we would say, or expected value of X. And something to take note of that's kind of easy to miss on this slide is this relationship. It says if we're dealing with a probability distribution, then the expected value of that distribution is the same thing as the mean of that distribution, mu. Okay? So the mean of a probability distribution and the expected value, those are the same thing. Okay? Then our formula, it looks maybe a little intimidating, but it's just because of the notation. We got the sigma and then we got the probability notation, so got a lot of maybe unfamiliar notation going on there, but all it says to do, it says to take each possible outcome, the top row of our table, multiply it by its probability, so the bottom row, and add all those up. That's the sigma. So each outcome times its probability, add all those up. Okay, so it's not hard. Not hard to do. So, questions on the formula, we're going to go back and find expected value for our coin flip table. Okay. If we go back to our coin flip table here, our expected value formula says we're going to take each one of these, multiply it by its probability. So we're going to say 0 times 1/8, 1 times 3/8, 2 times 3/8, 3 times 1/8, and then add all those up. Okay. So if I'm punching it in my calculator, writing it down, the way it's going to look for me, I'll have my first outcome, which was 0 heads, times its probability of 1/8, plus the next outcome was 1. It had a probability of 3/8. Plus my next outcome was 2. It had a probability of 3/8. Plus the last outcome was 3. It had a probability of 1/8. That's it. Okay. And if you had written them like decimals, you could use the decimal form there. Nothing wrong with that. The way I'm going to punch this in my calculator is 0 times 1 divided by 8, 1/8, plus 1 times 3 divided by 8, plus 2 times 3 divided by 8, plus 3 times 1 divided by 8 equals. Okay. You should get 1.5. Okay. Your calculator may give you, if you put it in as fractions, your calculator may give you 3/2. There's a button you can hit on most calculators that changes it to a decimal. If you need help finding that, let me know before you leave and I'll help you find that decimal button there. It usually looks like a S to D or something like that. There's a key on their standard form to decimal form. There's our expected value. So what's this telling me? The interpretation here is important. Okay, first of all, let's talk about what it's not telling me. And we can reason our way through that if we look at our possible outcomes. It's not telling me that if I do this experiment and I flip 3 coins, that I'm going to get 1.5 heads. Right? 1.5 is not an option. Right? What it is telling me is that if I do this experiment, I flip 3 coins a whole bunch of times, so maybe I do that experiment like 10,000 times or something like that. And I take the average of how many heads I got for all those experiments. On average, it's going to come out to 1.5. Really, technically, what it's telling us is if we do our experiment an infinite number of times, okay, but since you can't do something an infinite number of times, you can think about it just doing it a large number of times. Okay? So if we do our experiment a large number of times, on average, we can expect to get 1.5 heads per experiment. And again, we can kind of make sense out of that if we look back at our table. The 2 most common events are getting 1 head or 2 heads. Those are the most likely events to happen. And they have the same probability. So on average, you're either going to get 1 or 2. So it'll average out to 1.5. Okay. We're getting there. Okay. So expected value, you want to think about it as like a long-term average. Or long-term average outcome. Okay. Questions on that one? Long-term average outcome is what it says. I forget, this projector shines so low on the board in here. It was something with the beams in the ceiling. They couldn't get everything higher wherever I could see it. Okay, let's look at another expected value problem. Let me get to it here. We got some scrolling to do. Okay. Let's look at this one. So it says, suppose that Randall and Blake decide to make a friendly wager on the football game they're watching one afternoon. For every kick the kicker makes, Blake has to pay Randall $30. For every kick the kicker misses, Randall has to pay Blake $40. Okay. And then it gives us prior to this game, the kicker's made 18 of his past 23 kicks this season. So we've got 2 things to do here. Part A says, what's the expected value of Randall's bet for 1 kick? So that's where we will start. Okay. So if we need the expected value, we got to make a little table, like we did with the coin flips. And it's also important that we're thinking about this from Randall's perspective, because if we think about it from Blake's perspective, we'll have different numbers in our table. Okay, so let's make our table. We can need a random variable, and then we need the probability of a random variable taken on each value. So the two outcomes, and if the kicker's kicking a field goal, he either makes the kick or he misses. We want to think about the numbers of those two situations. So remember, when we're reading the problem, we're thinking about it from Randall's point of view. So if we go back to the problem, it says if the kicker makes the kick, what happens for Randall? It says Blake has to pay Randall $30. So from Randall's point of view, he just made $30. Right? So if the kicker makes the kick, Randall makes $30. Okay? So we can fill that in. I'm going to put that in as plus $30. Okay? If the kicker misses the kick, okay, so for every kick the kicker misses, Randall has to pay Blake $40. So from Randall's point of view, he just lost $40. So to represent a loss, I'm going to put it in as negative $40. Okay. So for Randall, these are the two possible outcomes. He either makes $30 or he loses $40. Okay. And then now to finish our table, we need the probabilities. So we don't have a lot of information to go on in this problem. All we have to work with is this last little part. It says the kicker has made 18 of his past 23 kicks this season. So if that's all the information we have, we're having to base our probability of the next kick on history. That's probably not the best way to do this if you're trying to like make a living. Okay? But for just working a homework or working a classwork problem, we're okay there. Okay. So it says historically, the kicker's made 18 of his past 23 kicks. So what can we use for the probability he makes the next kick? He's made 18 out of 23. So we can use that for our probability here. So it would be 18 out of 23. In reality, it's more complicated than that. Okay? You know, maybe it's snowing today and it hadn't snowed any of the other days. I mean, all kinds of stuff can come into play, but this is the simple version of getting a probability. Okay? Okay? So then what's the probability going to be that he misses? 5 out of 23. You can think about it a couple of different ways. Okay? If he made 18, that means he's missed 5 out of 23. Or we know we're trying to make a probability distribution. So when we add our probabilities up, what do they have to equal? They equal 1. Or in this case, 23 out of 23 would be 1. Okay? So there's our probability distribution. And then part A, question we're trying to answer, says find the expected value. So now that we've got the table, we're just using our expected value formula. So we take each outcome times its probability, add those together. So here we've got $30 times 18 out of 23 plus, and I'm writing it plus, you could do minus here if you wanted to. I'm going to do negative $40 times 5 out of 23. There's nothing wrong with just saying minus 40 times 5 out of 23 there. Okay. And then it's a calculator problem. Let's see what we get. 30 times 18 divided by 23. And then in my calculator, I'm going to do minus 40 times 5 divided by 23. That equals, you'd get $14.78. I believe, no, $14 and, yeah, $14.78. What it rounds to. It's money, so we can round to the nearest cent. Anybody else get that same number? Check me. Anybody else try it? Yeah, okay. So if you were Randall, should you make that bet? What's the expected value tell us? That's what I'm asking. Is this a good bet to make if you're Randall? Okay. Well, first of all, okay, we can start simple. Is our expected value positive or negative? Does that mean he should expect to win money or lose money? Win money. Okay. So we can go even a little further than that, because we don't just have a sign, we actually have a number. So our long-term average, if they made this bet a whole bunch of times, on average, he could expect to win about $14.78 per bet. Okay. Now that doesn't mean it's a guarantee, right? And that doesn't mean you can make the bet one time and win $14.78. That's not one of the possibilities. Right? But if they make this bet over and over and over and over again, on average, he can expect to make money. He can expect to make $14.78 per bet they made. Okay. So would Mr. Stanley make this bet? Yeah, I'd make that bet all day long. Okay. Positive expected value, that's a chance you want to take. If you go to the casino, you can set up a table like this for all the casino games. I mean, some of them will be really big tables, but you could do it. And then once you have that, you can calculate the expected value. What do you think the expected value looks like for games at the casino? You think they're positive or negative? Negative. Yeah, negative, all of them. Okay. Every game at the casino, okay, has a negative expected value if you're thinking about it from your perspective. Okay. What's that mean? That means if you play long enough, well, on average, you're gonna lose money. Okay. That's just a smart business plan from the casino's point of view. Okay. If you play long enough, they're gonna make money. Yes, they're in business to make money, okay, not to give it away. Now, does that mean you can't get lucky on the short term? Nope. Randall could get unlucky. If he made the bet one time, he could be out $40. Right? So luck still comes into play. Luck. Okay. You can still get lucky or unlucky, but on average, if you play long enough at the casino, you're going to lose money. And then usually I have somebody say, what about counting cards? Okay. So the idea there is if you don't count cards at blackjack, anybody seen the movie 21? No, it's too old now. That movie's too old for us. Okay. Anyway, the idea about counting cards is if you don't count cards playing blackjack, then the expected value is like negative 0.1 per dollar, okay, that you're betting. And if you do count cards, it shifts it to like positive 0.04 per dollar, 4 cents per dollar that you're betting there. So you can shift it in your favor. That's why it was such a big deal. But you also get blacklisted and you might get your legs broken. So probably not worth it. Okay? Questions on that one? Nothing? Okay. Oh, we do have part B, I forgot. Part B says, suppose the kicker attempts 4 kicks during the game, so they're going to make the bet 4 times. How much should you expect Randall to win in total? How can we figure that out? Well, the expected value is on average how much he can expect to win per bet. So if they make the bet 4 times, we just multiply. So part B, we just do 4 times $14.78. See what we get there. So if they make the bet 4 times, they can expect to win $59.12. What they did it 1,000 times. Then they could expect to win. You just move the zeros, and we just add the zeros around. That's why I said I would make that bet. Okay? If you can make it enough times, you're in good shape. Okay. All right. Next problem. Okay, we're winding down here. Next problem. Okay. Another way you can be asked these problems about expected value, you can have 2 tables like this, and then it can ask like which plan has the higher payout. So the higher payout there is just the same thing as expected value. Okay, so here to figure out which plan had the higher payout, we would just have to calculate the expected value of both tables and then see which one was bigger. Okay. We're kind of doing this on the way to answering another question, so I'm not just boring you making us do 2 more of these. We'll use this number in a second. Okay, so our expected value, and I'm going to put a little subscript A on here. Plan A. Do that formula, it'd be 45 times 0.21 plus 85 times 0.31 plus 100 times 0.48. So our expected value on this one is that 83.8, or since it's money, $83.80. For B, we do the same thing. So our first one's -5. Just because you have a negative on one and no negatives on the other one, don't jump to a conclusion that that one's necessarily going to be smaller than the other because it has a negative. It all really depends on the probabilities. So go ahead and do the calculation. It'll be -5 times 0.15, 80 times 0.54, plus 95 times 0.31. So what do we get there? On this one, we get $71.90. So that one did come out smaller, so there we would say plan A had the higher expected value. Okay. Or the higher payout, sorry, because it had the higher expected value. Okay. Questions on that one? This was just more of the same stuff we've been doing. Okay, so one more calculation we want to be able to make with these. And that's the standard deviation of one of these probability distributions. Okay. Remember the difference between standard deviation and variance. If we wanted variance, we just would not take the square root here. We're going to be more concerned with standard deviation. And if you look, we've got 2 versions of the formula. Okay. These 2 are equivalent. One's a little easier to do if you were doing it with like paper and pencil. And to me, one's a little easier to do doing it in your calculator. So since we're using calculators, to me, this version is a little bit easier, the middle one there, to type in. One thing to notice here, well, what's the formula telling us? It says we take each, it's almost like expected value to start with. It says we take each outcome and multiply it by its probability, but it's not just the outcome, it's the outcome squared. So each outcome squared times its probability, add all those up, and then we've got to subtract mu squared, and then take the square root. So we've got something we've got to remember here. This mu is the same thing as expected value. So to figure out standard deviation, first we have to calculate expected value. And we take each outcome squared times its probability, add all those up, subtract the expected value squared, and then take the square root. This one's a little bit harder to remember because it's got so much stuff going on. So this is the thing that'll be on the formula sheet. Okay? You just need to know what it's telling you to do. Okay? So our last calculation, we're just going to do one of these because they get a little long. And I think I only have like one in the homework. They're a little long because you have to calculate expected value first and then calculate standard deviation. So that's the reason why we went through and found E of X on plan A and B here. Okay. Remember, when we're dealing with money, we can think of standard deviation as risk. So this one asks us which plan A or plan B has more risk. So this is asking us which one has a larger standard deviation. So let's calculate the standard deviation for these two. So here on this one, our expected value was 8180, I believe. Is that right? Am I writing it now? 8380? Okay. So to find our standard deviation, our first outcome 45, but we need to square that number this time. And then multiply it by its probability. And then 85 squared times its probability. And then 100 squared times its probability. And when we get that figured out, we're gonna subtract our expected value that we've already calculated. So minus 8380 squared. And then we got one last step. Since it's standard deviation instead of variance, we take the square root. Okay. So a little tedious. I mean, it's just a calculator problem once you get it set up. Let's see, 45 squared times 0.21 plus 85 squared times 0.31 plus 100 squared times 0.48 minus 83.8 squared. So underneath the radical, just so you can check yourself, underneath the radical I got 442.86, but we still have to take the square root of that. So you should get, when you round to two decimal places because it's money, you should get 21.04. I believe on it. one more, we'll be done. Okay, on this one. Was this one 7190? Okay. So then standard deviation. B, you got to be a little bit careful on this first one because it's negative, so make sure you put it in parentheses when you square it. And then minus 7190 squared. We've got to take the square root. Let's see what we get there. So under the square root, I got 1087.89. So when you round at the end, 3298. Okay, so once you get there, which plan had more risk? Which plan had a bigger standard deviation? Plan B, it was 3298. The other one was 2104. So plan B has more risk, more risky. Questions on those? All right, I'll see you Thursday. Okay. If you try these and have calculator trouble, let me know and I'll be glad to help you on Thursday. Where did the sign-in sheet make it to? Is it up? Oh, back here? Okay. I'll put it on the table up front in case you missed it. Thank you.